So in this lesson, we're going to look at adding and subtracting vectors. Now, this is a section where most of our quizzes, we're going to have a really hard time doing them on SAM. So you'll find it'll be a little more giving me some paper or putting them online. So in this lesson, we want to look at what are vectors. I want you to be able to add and subtract vectors. Mostly, we're going to look mostly at just adding vectors. Subtracting them is pretty much the same. I want you to know how to break vectors into X and Y components. And I would like you to be able to, I have an extra outcome. You can ignore this. We can kind of ignore this last one, solve problems using vectors. I guess there are a couple problems here that involve that, but this solving problems is typically second semester that we deal with much of that. All right, so what is a vector? A vector is any quantity that has both magnitude and direction. That's the most important piece, magnitude and direction. We draw them using arrows. Direction we can give multiple ways. We can say, as the example here, okay, I've driven 15.6 kilometers northeast. Magnitude is the size, that's the 15.6 kilometers, and then the north is the direction. I could say the wind is blowing 4.65 meters per second northeast. You could talk about a current being south, or I could also use degrees from 0 in order to state the direction. So there's multiple ways we could say direction. Now in electricity, you're going to have it there. It's not really intuitive. You'll probably get most of that from Andy, but if you learn how to add vectors here when he gets to dealing with adding vectors to do phases in electricity, you'll be prepared nicely for that. Basic DC theory, I'm good with. AC theory, I've never really had a course on, so there's little bits I've picked up on the way, but I'll leave Andy to deal with most of that. So again, we're back at our quadrant system. So the first thing I want to think about is assigning directions. Now, if we look here, I threw a compass on here. So we have north, south, east, and west. So by tradition, north is always positive Y. E is always positive X, or east. West will always be negative, and south will always be negative. That is by convention. If you wish to change the convention, you will have to define your directions for me. So that might mean you have to draw me a compass somewhere so it says west is positive. If you live up west, you may find west being positive a really good idea, but you won't find a textbook that uses that, unfortunately. All right, so always looking at, so by convention, west, north positive, south negative, up positive, down negative, and then we have our left is negative, right is positive, east is positive, west is negative. So those are our conventions when we're assigning directions. Now, if we assign them using degrees, remember from before, the first quadrant takes us from 0 degrees to 90 degrees. The next one starts at 90 and takes us to 180 degrees. Here we do, and then here we go to 270 degrees. So 270, that's measuring from 0, and then takes us back to 360. Very rarely will we use negative degrees. If we say negative 13 degrees would be negative from 0 going the opposite direction. But traditionally, we start at 0, we go counterclockwise if we're going to use our directions using degrees. Now you will use a little bit of directions looking at degrees at the end of, well, I guess we're halfway through today's lesson. We're going to start without needing them. I'm going to get rid of my face here because you guys don't need that right now. All right. So when you're adding vectors, we're going to use the tip to tail vector sketching method. We're not going to use tip to tail to calculate them really, but we're going to use them to sketch them. So let's say I have these two vectors. The most important thing about vectors is they have to have the same length and they have to have the same direction. A vector can be moved anywhere as long as the length and the direction don't change. So that said, if I want to add these two vectors together, the tip to tail method says, let's say this is vector 1. Okay, I want the tip of this vector and the tail of vector 2 to connect. So we can do that. Oh, I guess I changed length. I change slides. You'll have to bear with me. Those are supposed to be the same lengths, and I didn't edit my slide. I'll edit it in the notes before I post them, but I need a little glitch here, so my apologies. So what we do to add them in the tip to tail method is we redraw the vectors and just resketch them, and I usually will use approximate sizes when I can. And we draw the first vector. At the end of this vector, I like to draw a little new XY plot. I pretend I've got a new graph. And then whatever this angle is, I want to keep the angle here and the angle here approximately the same. And then I draw my new vector. So that's a tip to tail. We've just shifted them around. That's our tip to tail vector addition. And then what we do is we draw a resultant. So this green line, this is our resultant, or the sum of those two vectors. So the green line is our final answer. And if you're red-green colorblind, my apologies. So these two vectors added together give us the resultant. And that sketch will help us figure out, well, what angle should we have for direction on this particular vector? We're going to look at more of that later in this lesson, but that helps us figure that out. It's also going to help us figure them out when they're in a single plane. All right. So first, you redraw your vectors. So the tip of one vector is on the tail of the other. Now we know if we add these two together, imagine they're pulls. Two people pulling on something. If it was two people pulling on something and their pulls add together, it makes sense that the pull's going to become larger in the upwards direction. And it's stronger towards the left than it is towards the right. So it makes sense that the overall pull, if it was an object, should go upwards and slightly, very slightly, should go upwards and very slightly towards the left. Okay, so, and we see that's exactly what we get when we add them together. Okay, so this is just our picture that we're going to use. Now, I will show you later how to calculate things using that picture when we get there. So, sorry, stolen picture, very poor quality. We'll upgrade this at some point later. So if we have parallel vectors, we have two vectors in the same direction. We just line them up tip to tail and add them together. So we have 3 plus 7 more, both in the right direction, gives us a vector of 10. Should really have units, and it's 10 in the positive direction. Here we have 10 plus -3. If I put those using tip to tail, if I take this vector, I'm going to resketch it. So I'm going to go 10. And then starting at the tip, I'm going to go -3 back. The resultant vector, that's my answer vector, is going to be, it's going to connect this tail to the tip of the second vector. 10 minus 3 would give me 7. So this vector happens to be 7 long. So you just literally, if they're in the same direction, we can just add them or just subtract them. We don't have to draw a picture out, but it can kind of help you visualize, especially if you're positive, negative number challenged. It happens. If you are, no worries. I almost quit university over a negative sign. So twice, or maybe more times. I forget how many times I threatened to quit university over missing negative signs. Upwards 4 gives us upwards 8 altogether. So if they're in the same direction, parallel vectors are nice and easy. So an example question, a trade-related question. Maybe not so much a trade-related question, but you have to have example questions at some point. You drive 84 kilometers east and then 35 kilometers west. Then you drive 12 kilometers east. How far from your starting position are you and in what direction? So let's sketch it out. 84 kilometers. All right, then I went west, 35 kilometers. Then I went back east, 12 kilometers. How far am I from where I started? Well, this is my starting point. I'll switch colors here and I'll draw my resultant in green. And this is my end point. So overall, this is the distance that I've gone. So in terms of signs, I went positive 84, I went negative 35, and then positive 12, leaves us with a total of, let's see if you can erase me with the calculator, 84 minus 35 plus 12, 61 kilometers. And what direction are you in? Well, you're still 81 kilometers east of where you started, or in the positive direction where you started. So parallel vectors are really, really easy vectors. We will do quite a bit of parallel vectors, and we'll do them, if we know how to do parallel vectors, we're going to do parallel vectors inside of more complicated questions that don't have parallel vectors. We're going to resolve our questions into simpler ones rather than doing some more complicated math. All right, so we don't always have parallel vectors. Sometimes we have right angle vectors. And right angle vectors are when we have two directions that are at 90 degrees to each other, like north and east are 90 degrees to each other. There's lots of ways we could do vectors at 90 degrees to each other. We're going to think of it in that XY plane. All right, so this question says, add these two vectors, give the magnitude and direction of the resultant. So I want to know the size and the direction. Well, how do you do that? Well, remember what I said about drawing them tip to tail. That's where we're going to start. If we can draw a picture tip to tail, as soon as you see that picture, you're going to know how to calculate it. I guarantee you, even if you've never seen vectors before in your life. Tip to tail, let's start with 6.2. All right, here's our 6.2. Then north, 4.5. You could draw the north first and then the east, and then the east, it wouldn't matter. The resultant, I'm not very good at drawing to scale here. Oh, learning exciting things here. It's not what I wanted to do, but interesting. We'll throw in our green color here. The resultant connects us from the tip of the first vector to the tail of the other. And it doesn't matter which way you drew them. If you went north first and then east, you're just going to draw, you'll still get this green line in exactly the same area. Okay? So you won't have to worry about that. All right, now that we have this, how do I figure out how big the resultant is? If you're thinking, Pythagorean theorem, I know this one. You do know this one. So now we're at a point where once I show you how to draw it, I don't have to teach you any more math. Technically, you know the math already. So the resultant is going to be a squared plus b squared equals, I'll call it our resultant squared, just to use that r in there. All right, so it's as simple as 4.5 squared plus 6.2 squared equals the resultant squared. I haven't calculated this ahead. Make sure you square things first. And we get 58.69 equals r squared. Take our square root. And r is equal to 7.66. Or, yeah, 7.66. I'll say we could even go 7.7 would probably be better rounding because we've got one decimal place on the rest. So that is the size of r. So the magnitude, all right, size, because I know I can spell it. The size of the vector is 7.7 kilometers. Now, what about the direction? Well, we could say, yeah, we could say northeast, but northeast how much? I mean, northeast is pretty vague. So for the direction, what we're going to do is we're going to say, well, this is 0 degrees here because we'll think of this like an XY graph. So this is like my X and this is like my Y. So 0 degrees is here. If I can find out what that angle is, I can give a really specific direction. I can say from 0 degrees, turn 30 degrees north. And that's my direction. 30 degrees from 0. So we'll figure that out. So to find our direction, and I really wish I had a position place things better. So to find the angle, we have 2 legs of our triangle. When we have 2 legs, we always use tangent. So if we label them, this is my adjacent, this is opposite, and tan of an angle is opposite over adjacent, which is equal to 4.5 over 6.2. What do you get for an angle? I'm not going to go through all the rearranging on that because I've run out of space. Maybe I will in the next one, but you should be almost experts at that. We get, what did you get? I get 36 degrees. So this angle in here is 36 degrees. So 36 degrees from 0. So that's a really specific size and distance, or size and direction for what would be the equivalent. Sometimes we use the term just because some people don't hear terms. There's terms that my grandmother used to use sometimes and people forget what they are. Let's talk about something, a distance as the crow flies. And that means instead of going around the sidewalk, cutting through the lawn. Okay? That usually gives a pretty good visual. So if you cut through the corner and just connect from beginning to end with a straight line, that would be the as the crow flies. You don't have to follow the road's distance. When we do vectors, that's always what we're getting. Overwhelmed you yet? I feel like I've been talking for hours. Maybe it's because I'm recording 2 lessons at once. If this is too long, please take a minute, pause, come back to it. Don't hesitate to do that. This can be a really good use of your time. Let's do the same thing. I got a couple more questions for you. I want you to add the following vectors. First thing, let's do a little sketch with what it's going to look like. This little sketch is just going to help us figure things out. I'm going to see if I can adjust. While I get started, you can start already because you've got some good skills already probably. 9.2. So you'll notice this time I've used degrees, the degree equivalents for their directions. Sometimes we'll give you these and we won't tell you what the arrows are. You should be able to draw them. And in Newton, that's what this N is. If you're wondering what that is, that's just like a pull. So we have one person, I'm going to use the word pull. We have one person pulling really, really hard towards the right and another one pulling downwards, but not quite so hard. And where is this box going to move? What direction is the force in? So we've got 9.2 and 3.7. I'm going to switch colors. I'll do the resultant in red this time. Our resultant vector is going to be this vector. So our red line is our resultant. The angle, there's our angle for our triangle. What do you notice about that angle? We'll see as you come along what you end up calculating for an angle. So the first thing we need to do is we need to calculate the resultant. So when we calculate the resultant, we're calculating the magnitude first. So we use our Pythagorean theorem. 9.2 squared plus 3.7 squared is equal to r squared. And we get 98.33 equals r squared. Use your algebra. Take your square root, and we get 9.9 equals r. So that's the size of our vector. So there's one part of our answer, but we're not done yet. That's not the whole answer. Now we need direction. So to find our direction, we have 2 legs. We know the hypotenuse, but we calculated that. We might have made a mistake in it, but we didn't make a mistake in the other 2. unless we copy numbers over. So we're going to use tangent. We typically will always use tangent. So the tan of our angle is equal to, tangent is opposite over adjacent. So the tan of our angle is equal to, the opposite side is 3.7 over 9.2. What do you get for your angle? Remember, this is a shift tan scenario. We get 21.9, which is 22 degrees. Now, we have to look back, and we're going to put those two pieces together in a final statement. I don't want you to assume you have your angle correct. Now, if we look here, is that 22 degrees from 0? Well, let's think about it. So we'll throw our little crosshairs in here. 0 is always the x line. So it's down 22 degrees. So we could say it's negative 22 degrees. Or we have to think, well, we were at 360 and we come back 22 degrees. 22 degrees would normally be on the top half of this. It's an equal fraction, equal triangle, has the same sides and same lengths. Now, we could get our calculator to give us a different answer if we adjusted something in our equation. I want you to try recalculating this. But instead of 3.7 over 9.2, I want you to use negative, because this 3.7 is down. I want you to use negative 3.7 and 9.2 to see what do you get for the angle. Negative sign you should be able to find on your calculator. Some people use a subtraction sign. That's going to give us trouble if you do that. And you get negative 22 degrees. So the negative 22 degrees would be from 0. Or we can say it's 360 minus 22. The equal would be, whoops, delete a couple things here. Or we could say it's 338 degrees. So the other way to say it's 338 degrees from 0 that way. So the answer, there's two ways you could say. We could say 9.9 newtons at 338 degrees, or 9.9 newtons at negative 22 degrees. So that's our final answer. So there's kind of a lot of little parts for these. I'll do one more question with you, and hopefully one more question is enough to kind of set you, actually it's two questions, one is a word problem. Hopefully it's enough to kind of solidify it for you and make it easily understood. All right, I have another 2 vectors to add. What's it going to be? So we have 4.2, 9.8. 4.2 is at 180 degrees, so we're pointing towards the west. And then 9.8 is pointing downwards at 270. So let's do a tip to tail sketch. I always draw my X first. So 4.2, and that's a negative 4.2 because of the direction it's in. If I don't conclude my 180, it's one way to get the calculator to assume direction. And then we're going to go downwards, negative 9.8. And there's my resultant. And I want to know what's the direction, and we'll put our crosshairs in. I want to be able to figure out, I want to change colors on purpose here, what is the direction and the length of this blue line. All right, so we'll do our calculations. Start it with Pythagorean theorem. So the magnitude of r is going to be equal to negative 4.2 squared. Negative times a negative gives you a positive. So if you want to leave the negative sign out in the equation, you can do that. Unless you remember to put brackets around things, it can cause a little bit of trouble sometimes, equals r squared. Now that we have that, we are going to plug it into our calculator, figure out r. So we get 113.68 equals r squared, and then we take the square root of both sides. Magnitude is equal to 10.7. And the units of this magnitude would be the same units as you put into your triangle. Now the direction. Well, we're using tan again. So if we use tan, there's my angle. This is the triangle. I need to know this piece in order to figure out the whole piece. So opposite and adjacent. So tan's TOA, so opposite first, so negative 98, or 9.8 over negative 4.2. Negative divided by a negative is going to cancel out to give us a positive. So what do we get for an angle? $67 degrees. Now let's stop and think about that before we give our final answer. Okay, our final answer needs size and direction. So R is equal to, well, we know it's 10.7 because the length isn't going to change at all. That's fine. 10.7 and it's in meters per second. So the overall, if this was wind, maybe you're in a boat traveling a distance and the wind is also pushing you, the overall speed would be 10.7 meters per second. At what direction? So when we calculate this tan, we found out 67 degrees belongs in here. But that's 67 degrees from, remember, this is 180 degrees in this direction. So we go 180 plus another 67, and that gives us our total. So we have to kind of correct our angles. So we only can draw a triangle. We can't do a full circle. So we have to think about the parts of the circle that are missing for it in our equation. So we're 107 meters per second at 240. I think I hit something funny in my calculator here for a second. So yeah, 180 plus 67, 247 degrees. Okay. Not too bad, hopefully. Hopefully. Please let me know if you have trouble with it. I kind of like to hear from you. You will need to know this, Randy, for January, so it's one of those pieces that you're gonna need. We're gonna spend about the equivalent of 4 days on working at vectors here, so that's kind of, I always finish with vectors, and usually things go quite well with it when we start back up in January. All right, one last question. Oops, one last question. A plane is flying with a speed of 150 kilometers an hour west. That's probably really low speed. This is what happens when you make questions up. There's also a crosswind of 80 kilometers per hour. So what's the resultant speed? Maybe it's a glide. So it's flying west. So we've got the plane in the right direction. So we've got 150 kilometers per hour. And then we've got a wind south pushing down on it of 80. Okay, so I always like to kind of throw things in a little sketch and then I do my tip to tail. So I'm going west 150 and I'm going down negative 80. What is the resultant going to be? And I can tell by looking at it, even before I start calculating, I'm going to have to correct this angle because it's not in quadrant 1, it's in one of the other quadrants. The triangle includes, the angle I want includes 180 degrees that aren't inside the triangle because I want to go from 0. So I was going to think, where did my triangle get drawn from? So let's do some calculating. Let's calculate the size. So 150, negative 150 squared, plus negative 80 squared equals our resultant squared. So we get 28900 equals the resultant squared. Take your square roots. 170 equals our resultant. Now that we have that, direction. You'll notice our direction always uses tan. We're always good. You could use cosine, but if you've made a mistake, or sine, if you've made a mistake on calculating your size, calculating your R value here, then you've made a mistake. You could have made a potentially bigger or more hazardous mistake. So typically we'll use what was given in the question. So we're going to use tan of the angle. That's this angle inside the triangle only. So the tan of the angle is opposite, which is negative 80 over negative 50, or 150, sorry. So our angle is equal to keep some extra decimals when if you're calculating this middle step, which is equal to 28 degrees. So the total resultant, so that's a resultant speed. The resultant speed is equal to 170 kilometers per hour. That's why you land a little faster when there's a wind. But it's at 28 or 180 plus 28, which gives us 208 degrees. Okay, so this plus 180, this 180 comes from that extra half a circle there. Okay, hopefully you can follow that crazy math. Hopefully that wasn't too bad for you. We're going to do a couple more next class. Next class we'll say, okay, you've done two vectors at right angles. We're going to do non-right angle vectors. And then we'll throw in, well, what if we have three vectors, like a three-phase circuit has three vectors. If we have three phases, like Andy's going to give you, what are you going to do then? If you know how to do two, you're going to know how to do three. And if you know how to do these ones, you're going to know how to do two vectors, not at right angles, because we're going to turn everything into a right angle triangle. All right, there's going to be a little assignment to go with this section. I'm going to give it to you, I think, as paper assignment, because I think it'll be a little easier to see. Sam doesn't handle this stuff very well. And we'll go from there.